Hi, AP Calculus students. Welcome to section 6.1, differential equations. The cool thing about this section, I'm on the wrong side. The cool thing about this section is you have already done a lot with differential equations, so a lot of this will not be new to you. So, however, we usually in class read over pages 406 to 408 together. So if you could please do that. But here are some highlights from that reading. A differential equation, as you know, has derivatives in it. So to solve a differential equation is to remove the derivatives by integration. So you have a function in terms of y or f of x, or in terms of x and y, I should say. See, a general or a family of solutions for a differential equation is when you have y equals an equation with the plus c, right? That will create a family of equations. So a particular or singular solution is when you find a value for that plus c. We've done that before, using a given point, or they'll call it an initial condition. Euler's method is in this section. It is in BC, not AB. So after the AP exam, after a little break for other AP exams, college exams, things like that, we will study Euler's if you wish. It is really cool. And it is, if you remember in the movie Hidden Figures, it actually is how they got those astronauts back home, was using Euler's method. So examples, we're going to do 2, 32, 54, and one like 61, 63. And this is the example I'm going to do. So what I found in this section is their wording isn't the best. So you have to read carefully about what they actually want you to do. And sometimes they give you more information than you need. So let's look at number 2. And number 2, we've done this before, where you have been given, I put diffie-q, that is a differential equation. There's a whole course on differential equations in college, fondly called diffie-qs. So here they are saying in your book on number 2 that this equation, this function is a solution to that differential equation, and just to prove that that is true. So you've done it before. So notice my y will go here, but I also need the derivative of y. So let's get that. The derivative of y is of e to the negative 2x, of course, is itself, and by the chain rule times the derivative of the inside function. And now we're just going to substitute our differential first derivative here in the function there. And we have 3, negative 2 e to the negative 2x plus 5 e to the negative 2x. And apparently that equals negative e to the negative 2x. We'll take a look. You can see that's true. You have a negative 6 of e to the negative 2x here. You have 5 of them here. When you add them up, you have a negative 1 of those. And this is in fact true. And that was your only job. Okay. On number 32, same thing, except the wording is where they give you a solution equation. They give you a differential equation, and they give you a picture of a family of equations. But in that graph with the family of equations, they give you the 0.34, and they ask you to find the particular solution to this general solution. I would have thought that they would have asked you to do what was above that to prove that this is a solution of this differential equation. They do not. They give it to you anyway. Of course, they just ask you to use this 0.3 and 4 right in the solution to solve for C. It's really all they're asking for. So let's go ahead and do that. So this would be, when I put a 3 in here, that would be 9 times 2, obviously 18, minus y squared minus 16 equals C. Obviously, my C equals 2. And that was literally all they wanted from you. Okay. You may want to fast forward while I erase. I always say I could pause, but I'm so afraid I won't turn it back on and then be talking here for nothing. Okay. Because number 54 and numbers like 61, 63 takes a little bit to set up. So on number 54, you could certainly look in your book They give you a lot, but don't ask you for much. So here's what they give you in your book. It's going to give myself some room here. They give you x and y and dy dx. So dy dx is slope. At a point, it's a change in y with respect to x, right? And I hope I write these points right. They give you -4 and 2, -2 and 0, and 0 and 4, 2, 4, 4, 6, and I just am missing an 8, 8. Okay, and on 54, they give you the differential equation is y minus x. Okay, they also give you a slope field. You'll see on number 54 right here that goes with it. And it's pretty cool. For any point that you pick, any XY point that you pick on that slope field, when you put that XY in here, it will give you the slope. And when you look at that point on the slope field, you will see a little tangent line with that slope. Now, their actual question, a differential equation and its slope field are given. Complete the table by determining the slopes, if possible, in the slope field at the given points. So all they're giving us a set of XY points, and they just want us to fill in the table. They're not even asking us to draw on the slope field like they usually do. Now, I know this seems weird, but I am much better with this slope equation if I put the X followed by the Y, so -x plus Y, right? So when I read the XY point, I read it well. Okay, so let's put in a -4. I'm putting in the point -4, 2, right? And I get a 6 out, right? In other words, if you look on your slope field, if you go to the point -4, 2, you will see a very steep positive slope there. That's supposed to be 6. Let's go to the point -2, 0. Is a 2. Right, again, one last time. If you go to the point -2, 0 on your slope field, you should see a positive slope of about 2. 0, 4 is 4. 2, 4 is 2. 4, 6 is 2. And 8, 8. There we go. Even though they gave you all kinds of stuff, they only asked you to fill in the table. Okay, I'm going to erase. Like 61 or 63, they do ask for a bit more here. So here's my, so this is like 61, 63. Here's my differential equation that I made myself. X plus Y. Okay, and what they were asking for in bold, sketch the slope field for the differential equation. Okay, so what I'm going to do, I'm just going to go 2 each way. I could go like 3 each way or 4, but that's a lot of points, right? 4 times 4 is 16, 3 times 3 is 9. Here, I'm just going to go to 2 by 2. You know what? It might be easier though. You know what? Let's do 3. It's our first one, making our own slope field, isn't it? That's not that bad. Let's go ahead and do that, okay? Then they want to know, use the slope field to sketch a solution through the given point. So slope field and then sketch solution through a given point, and mine's going to be 1, 1. Okay, and they also want to know what's happening on the ends, the left end and right end. So they're saying they want to know as x approaches infinity, that's to the right, what we believe is happening, and as x approaches negative infinity. Almost asking limits, like what is the limit of the function represented in the slope field as x approaches negative infinity and positive infinity. So it's like a limit. So we will answer this also. Okay, here we go. So I usually start at the origin. So notice at the point 0, 0, when I put a 0 in, 0 plus 0, the slope is 0, horizontal line. Okay, now you can go any way you want. I just tend to, I'll go up and down the y-axis, then go to the right and go to the left. 0, 1, when I put in 0, 1, 0, 2, right? And so you kind of get the hang of it, is as the y's, if x is 0, as the y's go up 1, so does the slope. So I just keep making it positive, little steeper. This is 0, negative 1, so that's a negative slope. And as y gets lower, it becomes more and more negative. Okay, let's go to 1, 0. The slope is 1, right? And as y goes up, the slope gets more and more positive, right? So 1, 1. And again, it's really just doing your best. Mine almost looks the same, like I should have tried to make it more steep, you know. 2, 0, then steep. Steeper, steeper, steeper. 3, 0 starts out pretty steep, more steep, more steep, more steep, right? So this is all, because the x's and y's are positive, those are all positive slopes and they get more steep as you go to the right and up. Let's take a look here at 1 and negative 1. Notice that you have a 0 there, right? And now when you have 1 and negative 2, right, it's negative 1, and then one more down is more negative. Let's go over to 2, negative 1, that's a slope of 1, right? At 2, negative 2, a slope is 0, right? And then one more down makes that a negative slope, right? So we're kind of getting the hang of where those tangent lines are. That's 0, right? Because that's wherever the x and the y have opposite signs, right? So at 3, negative 1, right, that's a slope of 2, slope of 1, and then at 3, negative 3, a slope is 0. So we can kind of see that, you know, the horizontal slopes go like this. Kind of fun once you start getting the pattern to fill it in. Negative 1, 0, right, is a negative slope, 0, and then as you go up, it's up a slope of 1 and a slope of 2, right? Start getting the hang of it. At negative 2, 0, that's a negative 2, right? Then up 1 would be a negative 1, 0, and then a positive 1. Negative 3, right? Negative, less negative, and then 0. Let's take care of this quadrant here. Negative 1 has a slope of negative 2, and as the y goes down, so does, it becomes more negative and steeper. Negative 2, right, and as the y goes down, it keeps getting more and more negative. And same here, right, just more and more negative. All right, so we made our slope field, kind of fun, I think. Let's graph the point 1, 1. That is right here. And they want us to draw a general solution through here. So I'm going to go to the right. My slope fields seem to be guiding me this way. Maybe I could have snuck through. Again, it's just a sketch. And my slope fields this way seem to be guiding me right here, and then horizontal kind of here, and then guiding me up on the left side also. So it would appear that as x approaches infinity, so does our y values, and as x approaches negative infinity, so does our y values. So, and that is section 6.1. Again, kind of cool since you already knew a lot. Have a great day.